Okay, so this video is going to be the first of a couple on the unit of equilibria. Chemical equilibrium, it's quite nicely being represented by this diagram here. Okay, so you start off with two reactants, A and B, and as they collide and react together, then they form the product molecules C and D. As time progresses, you get more of the products being formed and less of the reactants, until eventually you get to some sort of equilibrium position. Now it could be that there is an equal distribution of A and B to C and D, as it looks to be kind of like here, or it could be that you got more products, which looks to be the situation in this case. Okay, what we are going to look at here is how do we get there and how can we affect the position of the equilibrium. So an equilibrium in a chemical reaction is classed as a dynamic equilibrium. So dynamic means that something is always occurring. It is the opposite of static. So a dynamic means constant motion. So in a dynamic equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. And this means that the concentrations of the reactants and the products will remain the same. Now, for a system to be in a dynamic equilibrium, it has to have the following features. It has to be in a closed system. So you can't have an open beaker where one of your products is a gas and it bubbles off into the atmosphere. The rate of the forward reaction must be equal to the rate of the reverse reaction, and the concentrations of the reactants and products remains constant. So, how do we get to equilibrium? So we saw the picture on the front page, which showed that we started off with a high concentration of our reactants and a zero concentration of our products. So if we consider this equilibrium here, the blue line represents the reactant, N2O4. The red line represents the product, NO2. What we see here is that initially at time zero, a high concentration of N2O4, zero concentration of NO2. As time progresses, the N2O4 decomposes, and as it decomposes, it releases molecules of NO2. There then comes a point where there's more NO2 than there is N2O4, and then when we reach this dotted line, we have equilibrium. Okay. Now, what's happening here is at the start of this chemical reaction, the rate of reaction is at its fastest. Okay. As the gradient decreases in this blue line, the reaction is slowing down. Conversely, this formation of the NO2 is increasing all the time until it gets to this point where it starts to taper off and the gradient becomes less and less, and we reach a point where we have a zero gradient, and this means that the concentrations of the NO2 and the N2O4 are exactly the same, and this means that the rate of the forward and the reverse reactions are exactly the same. Now, we can change the position of an equilibrium. We can do it a number of ways, either using concentration, using pressure, or using temperature. Or we can predict how changing one of these things would affect the position of an equilibrium by using Le Chatelier's principle. Okay, so Le Chatellier's principle basically is the position of the equilibrium will shift so as to minimize the effect of any change in the conditions. So for example, if you increase the concentration of a reactant, it will react in such a way as to decrease those increased concentration of reactants. Okay, so let's have a look at some examples. Okay, so we've got ethanol and propanoic acid reacting to form ethyl propanoate and water. This chemical is called an ester. The trouble with this reaction is that it lies in equilibrium. So, generally you want to make more of the products. That's the whole point of you doing a reaction. So, according to Le Chatelier's principle, if we increase the concentration of, say, the ethanol or the propanoic acid, either of these reactants, then the position of the equilibrium will shift in the direction that decreases this increased reactant concentration. So in this case, if we've got a high concentration of ethanol, then the equilibrium will shift to the right hand side towards the products to offset the increasing ethanol concentration. If we were to, say, add more water to this equilibrium, the effect would be to shift the equilibrium in the reverse direction, so the equilibrium would shift to the left to offset the increasing water concentration. Okay. Similarly, you can think about it the other way. If you decrease the concentration of ethyl propanoate or water, then if you reduce the amount of water on the left hand side, then you would drive the reaction to the right. Okay, the equilibrium would shift to the right hand side to create more water to compensate for that you have removed. Again, similarly, if you decrease the concentration of, say, propanoic acid this time, the equilibrium will shift in the reverse direction, shift to the left to create more propanoic acid. Okay. So, looking at a question like this, what would be the effect of adding more HCl on the position of the following equilibrium? HCl is a source of hydrogen ions. Okay, so what would happen is that you would increase the concentration of the hydrogen ions initially. The equilibrium then reacts, and it shifts to the right hand side, and so that the colour of the reaction now turns more orange, or it turns darker, because the equilibrium is trying to minimise the increase in hydrogen ion concentration. Okay, if we've got gases, and again, the famous reaction you know with gases is the Haber process for making ammonia. If you increase the pressure of the system, this causes the position of the equilibrium to shift to the side with fewer moles of gas. Okay, because this will decrease the pressure. So increasing the pressure in this reaction, because you've got 4 moles on the left hand side, 2 moles on the right hand side, increasing the pressure would drive the equilibrium to the right, or it shifts to the right to minimise that increase in pressure. Okay. And the reason for that is because there are fewer moles of gas on the right hand side. If we were to decrease the pressure of the whole system, then to offset that change, the equilibrium would shift to the left where there are more moles of gas. Okay, so another example would be here, question 5. You've got N2O4 and NO2 in equilibrium. N2O4 is colourless, NO2 is brown. The pressure, if you increase the pressure of this reaction mixture, well, it's going to go, the equilibrium is going to shift to the side with the fewer moles of gas. So it's going to shift to the left, and therefore what you would observe is that the reaction mixture would go lighter in colour or paler in colour. Okay. Okay. Temperature. Now, temperature, slightly trickier, is this. You will be given a reaction and you will be given an enthalpy change. The enthalpy change is for the forward reaction only. So, the effect of changing the direction depends upon the enthalpy sign. So you need to be sure of these. So, a negative enthalpy sign means it's exothermic in the forward direction, going from left to right. If it's got a positive value, it means it's an endothermic reaction. And that's again, going from left to right. Once you have identified which of the forward or reverse reactions is exothermic, then it becomes more straightforward. So, according to Le Chatelier's principle, if we increase the temperature of the system, the equilibrium will shift to the side that decreases the pressure, i.e., it shifts the reaction in the endothermic direction because that absorbs the heat energy. So in this case, increasing the temperature shifts this equilibrium to the left because the reverse reaction is endothermic. If you were to decrease this reaction temperature, the effect would be to shift the equilibrium to the right towards the product because the forward reaction is exothermic. And that's usually all you need to say to get your marks in the exam. Okay, so here we've got this equilibrium. We've got a pink solution here. We've got a blue solution on the right hand side. The enthalpy change is positive. So it's positive, it means it's endothermic. So if you increase the temperature, the effect on the position of the equilibrium will shift to the right in the forward direction. And so the solution would end up looking more blue in colour. Okay, and then the final thing I just want to say is this. The effect of a catalyst on the position of an equilibrium. A catalyst has no effect on the position of the equilibrium because the catalyst speeds up the rate of the forward and the reverse reactions equally. The only use of a catalyst is to increase the rate at which the equilibrium is established. So again, that's usually a banana skin question that they slip in sometimes. So don't fall for that one. Okay, the next video will look at Kc, the equilibrium constant.